This talk takes two subjects. For one side, we have the concept of machines or computers, but I have a special interest to illustrate this subject with robots, and later how connect the problem of learning with these machines that will be compute some Turing machine equivalent. Okay, before I want to thank several collaborators around the world. Her contributions and participation for several collaborations from Adamaski, Ricardo, Macintosh, Ivan, Sergio, Bruce, Shigeru, Kenichi, Maurice, Marcin, Ivan, Dimitri, and several of those results comes from several years ago. Okay, what is the main interest? Well, we will discuss how a machine, in this case robots, can be able to perform computations and what imply the problem of learn in these machines. So I have interest in this subject because several years I have worked with robots and trying to understand how a robot can perform a specific task following several algorithms or any other techniques. Of course, this problem is related to artificial life, artificial intelligence, and machines. So, particularly, I have a special attention in modular robots and the serial automata theory. Okay, why consider the serial automata theory? Well, in principle, we have here concepts of natural, simple programs, discrete domain, and parallel computation. Indeed, Edward Fairchild in 1992 conjectured a principal problem that is known now as finite nature. Finite nature related problem that probably the final goal is that all domain will be discrete. Under this assumption, the serial automata is an ideal model to study these implications. Well, some motivations and ideas. From the conception of serial automata, von Neumann recognized this problem where the cellular space can be exploited for using the results of Turing, particularly the universal computing that can be modeling in these cellular systems. In this direction, if you have a cellular automata, a parallel system, then we can think to implement a Turing machine. Of course, we have several ways to design and perform cellular machine. Then we evolve and process signals, sometimes gliders or particles in the evolution space. And of course, simulating any Turing machines, we can walk to the universality. In this direction, von Neumann himself introduced several interesting concepts, such as the problem of the universality in the cellular automata theory, the problem of the cellular production organisms in this cellular space, And a complicated concept that is the universal constructor, because the universal constructors specify anything in the universe, not only the Turing machines, because the universal constructor could be able to construct anything in this universe. However, some years later of these results from von Neumann, Edward Moore proved that some configurations in these universes can be not possible to construct. That is a great problem for several things. The other interesting problem established from von Neumann was how we construct reliable organisms from unreliable components. It is a central problem in many complex systems, because you can work with primitive organisms. The problem is how organize these elements, these primitive elements, to perform a specific task, right? For example, if you want to design a specific algorithm, so it's necessary think how design the evolution, the cellular space to control the signals, and therefore implement some algorithms. Okay. Following these motivations, I remember several talks with Professor Harold McIntosh. Sometimes talking with him some years ago. In a time in his life, McIntosh had the opportunity to meet with von Neumann in Princeton. And in these sessions, hear many times how von Neumann was interested to the possibility of construct factories automatically. Of course, not necessarily in a physics form, but in artificial directions, how some factory could be the characteristic of cell reproduction. Following the idea using cellular automata, McIntosh has commented several times, for example, how watch the evolution when you see the dynamics of particular cellular automata. Maybe it's not easy to understand what is the dynamics, because several times it is the origin of a great deal of confusion. In this direction, of course, several techniques are used in cellular automata to understand the dynamics, chaotic behavior, or complex dynamics. Okay, I will back to two historical papers relating this problem. The first, because these problems are not new, really. For example, Alan Turing in 1950 year establishes a question: can machines think? Well, Turing discussed amply this problem in this paper, that is the computing mechanism and intelligence. And in several stages in the paper, Turing establishes this difference between computers and intelligence. So a conclusion is that, of course, we will separate these concepts to try to specify what is the relation between the intelligence in computer science. Because of course, affinity state machines is able to perform many tasks. However, these machines have not the ability to think. That is impossible to relate in the concept of intelligence and the humans use it commonly. The other paper comes with Marvin Minsky in 1961. In this paper, Minsky establishes 4 properties for talk about of the artificial intelligence. Minsky separates 4 components here, and principally the problem of learning systems. How an artificial system can be the possibility to learn. So Minsky discusses in several paragraphs that this problem is related to the fact where a number of actions, of experiments, will be this learning situation. However, Minsky separates the other problems, that is the information and the feedback problem, and so on. Okay, we know, of course, for several years, and if we talk about the computations, we will relate immediately the concept of algorithm, because the algorithm is the description of a problem in these steps. Okay. A consequence of computation is what problem can be decidable or not. Well, of course, Alan Turing solved this problem with his method, specifying if we have a problem, this problem will be evaluated in a finite state machine. That is indeed the Turing machine itself. So if this problem can be described for a number of steps and reach a final state into this machine, okay, we can conclude that the problem is decidable. In other case, the problem is not undecidable, and the main problem is that we cannot develop any algorithm in this direction. Okay, here we have a simple experiment. In our laboratories, we construct a simple robot, the e-bot. This robot has only 2 parameters, because this robot has only sensors, distance sensors, and only takes 2 decisions to walk into the surface. But what happened with this robot reached some complicated places into the laboratory? Well, the robot will be decide what is the action to exit in this gate. In this direction, we can think about of artificial disability, because it is not really complicated how the robot is able to find a solution for this problem. And the robot can work for many hours in this room, including the robot not collapse really, because the sensors permit specific distances, and this avoid that the robot could be reached very close gap into the laboratory. Okay, so we can say that using only two simple decisions, the robot can survive for many times in the laboratory. Okay. Learning in machines. Well, learning depends on the history and facts for organisms, life organisms. And this change dynamically. It is the experience. But for a robot, it is a database and a number, and a number that is the number of experiments in these robots. This is the frequency where the frequency more the database is useful to talk about of learning in machines. Okay, now we have particular interest in modular robotics. Why? Well, modular robotics are cheaper in some direction. They are versatile, work in blocks. That is very useful to reconfigure many robots with the same components. They are reconfigurable and are adaptable for new designs and can be useful to solve other problems. Particularly, we will work with Cubeless robots. Cubeless robots are invented for Eric Streikert, that is a graduate of Cornell University. No, Carnegie Mellon University in the United States. And those robots work with magnetic properties because you can connect the robots only concatenating these magnetic phases. And you can think on several designs. Particularly, we have an ample number of possibilities because if these robots only need a concatenation or juxtaposition, so we have an infinite number of robots because we can't work with robots in 1 dimension, in 2 dimensions, in 3 dimensions, and only we need specify what kind of robot we need. In this case, the Cubeless robots have 3 essential characteristics. One set of robots are the sense, action, that is the distances, brightness, knob, or temperature. The other block are considered for think. It is the interesting characterization of this robot because the think block relates the battery, the Bluetooth connection, passive robots that have not any action, blockers, inverse, maximum, minimum, and threshold. And finally, we have the set of action robots. They introduce the mobility, the dynamics in these robots. And they are the rotate actions, the driver, the bar graph, speaker, and flashlight. So this notation is useful to codify and construct specific robots where we can reconstruct easily. Where is the mouse? Okay. Actually, we have designed some robots in our laboratories. A typical example is the autonomous car, where this autonomous car is constructed basically with a sensor in the front of the robots and impulsed for 2 drivers Cubeless robots. What is the idea here? Well, the robot is able to take decisions and following several ways. Of course, in an initial state, the robot is recognizing what is the area. So when the robot is working, the robot again will decide what is the best action here. For example, following a simple problem where the robot will be find the best way to reach the start and end state. The robot will be again store what is the route where it's working in the time, and later decide what is the best change in the direction. Of course, when the robot is working for several minutes, it is information is stored in a database. So the database again is useful to establish in the robot what is the best next decision. So actually, we have other models where we can connect, for example, cameras, where the camera is useful to recognize different views from different perspectives. What is the problem here and the utility is that you can analyze different kinds of views at the same time. For example, using a 360 degrees view. So this information is useful to recognize, of course, the environment and the objects and the surfaces and inclusively aerial objects, right? Okay. However, what happened with these robots? Well, another interesting implementation was robotic Turing machines. We have reports about of mechanical Turing machines, or for example, the Lego Turing machine that some years ago was implemented for the Lego company. However, here we exploit the versatility of cubelets and implement a Universalturing Machine. This Turing machine relates the problem of several automata rule 110, and the machines has the action where will be simulate the dynamics of rule 110. Of course, the dynamics is visualized of one array of blocks, and the machine is able to advance and read the characters. We will see how it works, the machine. Okay. The machine basically use two simple actions. One action is move left or right. That is the original concept of a Turing machine. So one sensor, that is the Cubeless robot that is in the front. This sensor is that captures what is the binary value in the tape. The tape is characterized by blocks of Lego pieces, but the Turing machine is implemented in this rotator action. The rotator moves the the branch and decide if the value will be changed or not. In this case, the binary value only is determined for the position of the block in the tape. If the position is near of the machine, so the value is 0. In other case, the value is 1. So consequently, we have a question here. Particularly, this machine is able to understand the action because this robot simulates a Universalturing Machine. However, of course, the robot cannot understand in essential the concept of universality. Only perform a task. Okay, so returning to the concepts of computer science, historically, we have the problem that if we have, for example, a Turing machine, well, how this machine could be represented in other systems. For example, in nature, if plants or trees are dominated for small Turing machines that can perform some specific or small task to reproduce a plant, for example, or any other action in the natural. For example, pigmentations in the animals or some other simple tasks. Well, in computer science, we have these translations commonly. For example, we have a Turing machine that we can translate to cellular automata. What is the problem to do these translations? Well, the translations could be implies in more states, in more relations for the new machines. But of course, they are equivalent to produce the same computational capacities. So the inverse case is similar, where you can take, for example, cellular automata and try to implement a Turing machines into the evolution space. Well, following this idea, thinking about of this equivalence between machines and their conversions, here we can see the dynamics, the Turing machines that was illustrated with the Cubeless Robots. But here we can see a color representation of the same Turing machine, where, well, in this case, for artistic reasons, the stable background is the purple color, but color red is number 1 and color yellow is number 0. So looking the picture, we can try to recognize some patterns in the evolution. Of course, it is other problem because the patterns correlate some possible solution in the dynamics of the Turing machines. But actually, you can explore Turing machines in 2 dimensions because only need specified colors for the Turing machines and concatenate the string, the tape every time, like a cellular automata dynamics. What is the main problem to look dynamics in cellular automata and Turing machines? Well, in the first time, it is the time, because at Turing machines we need many steps where you can possibly find some patterns, where in servo automata it's more fast to recognize. Okay. In the same direction, we can explore some evolutionary rules in 2 dimensions. Of course, we know that the computation works in 1 dimension. Indeed, the Turing machines works in 1 dimension, the post systems, anyway. However, works with computers in 2 dimensions offers other possibilities, where the parallel computation will exploit immediately. In this case, we illustrate and lifelike rule B2S2345, where this evolution rule exploit in chaos. That is different to for example, the famous The Game of Life, so automata invented by Conway in 1917 year. Well, how here the problem is how we can construct a computable system into this chaotic system. Well, in this evolution, we can see how a swarm of a specific configuration that are represented for this square are stable. You can increase the number of these patterns and the universe will be permanent stable. What happens if you introduce some virus of noise in this array? Well, the main characteristic is the array will be permanent fixed. That is no perturbed for the system. That is an important characteristic to think in another possibility. Particularly with this automaton, we can recover some ideas from Neumann. We want codify binary values, but not only by single signals. And here we can think about biology or chemical reaction, where a set of states, in this case, these patterns are stimulated for one collision between a particle that is traveling versus the wall, and the collision produces an explosion of patterns in the evolution space. In this case, we have a simple principle. If the pattern is symmetric, then this value is 0. But the pattern is asymmetric, and then the value will be 1. So following this simple principle, we can control information in this chaotic automaton. Recently, indeed this year, we have implemented a 3 input majority gate. What is the characteristic in this majority gate? Well, in the first time, the majority gate implies a parallel computation because the 3 values will be processed at the same time in only one position. That is exactly the middle intersection between 3 channels, where the channels are traveling with the qualification of binary values, and we have implemented all combinations, and we will produce the truth table for this majority gate. Okay. Actually, this designs with this majority gates is used in nano computing or another electronic implementations. following the same ideas, we have an implementation with robots. In this case, we have not designed robots that have the capacity of moving. In this case, exploit another characteristic. Because robots, Cubeless robots with the capacity to propagate light, depending what is the value into the internal Cubeless robot, this way we can simulate a binary value. A binary, a full adder. This adder have 3 inputs, that is A, B, and Z. Particularly, this adder works only with majority gates and helps with some NOT gates to consolidate the final operations and produce the addition of the combination of values and preserve what is the carry value that we will preserve in the operation. Of course, the design is not probably the most optimal implementation because we need to specify the value A and B with 2 Cubelet sensors. However, we can connect these inputs with using more robots. But the final result here is that the propagation of light into this design produce exactly the action of this full adder. So every combination is calculated for the reaction for every robot, and the robot propagates the actions for the binary value. Finally, this robot is able to simulate this algorithm. Okay. What we conclude? Well, we have a number of questions given the experience to work with the robots and servo automata rules, and we can specify some sentences. First, a computer could choose an algorithm itself. Well, theoretically, it is true, because well, is here a way to get this algorithm? Is this intelligence? No, because the intelligence is different to the number of experience to get a final result. Well, what happened with the same computer? The computer could find this solution into the universe of possible solutions. Yes, it is possible in the universe, possible solutions. It is intelligence? No. So what is? It is randomness. Because the universe of possible solutions, the universe of algorithms, we know is infinite. And the possibility where a computer by itself could find this solution or algorithms is possible into the universe of randomness. But what is the problem? The problem is that the probability is very slow, where this computer could find by itself the solution. Okay, could a universal algorithm find and execute another universal algorithm? Yes, this is problem. But the problem again, the probability is very slow. Well, what happened with robots? Is this learning? If we remember that learning is a sum of experience, this is true using a database of some finite state machines, some neural network, for example, but different with the human concept of learning. So thank you very much for attention. And if you have any question, I will be very happy to attend. Thank you.
Thank you very much. This was very interesting talk, and I think it stimulates a lot of reflection and possibly questions. So I would like to, Genaro, can you unshare your screen, because then we can show participants. If you unshare your screen.
Okay.
And then I'll ask. So I would like to encourage questions. So to Genaro.
Yes.
Are there any questions? You can, for questions, I will ask you. You can raise your hand. On at the bottom, you will see there is reactions. When you open the reactions, you can click on raising hand. So for instance, here I click and my raise hand appears. At the moment, I don't see yet any questions, so maybe I will use this opportunity to ask my question.
Okay.
My first question is about your last comments were about learning. Yeah, definitely we have some form of learning in this case, but then in discussions about learning, not in the context of automata, not in the context of computing, but in general, there is this idea that there is difference between learning and active learning. Can you see a possibility that automata, cellular automata, or any form of computing system can acquire this ability of active learning, not as a reaction to stimulus from the environment and like learning, collecting a lot of information, but seeking information. What do you think about this way of learning by automata?
Well, again, as you have commented, it is different to the human concept or human experience, because I remember, for example, a typical problem where a child tried to walk in the first months of the life. So the child can't understand that he needs to move the legs in some frequency and force to get the energy to motivate this learning. However, for machines, it is only I think, for example, if the robot is able to collect a specific algorithm and decide what is the best algorithm to perform and try to work. However, what is the final decision for the robot? The final decision for the robot is that if its dynamics have not any perturbation, the algorithm works fine. But if it is not the case, so the robot has the possibility to select another algorithm with some small change and intent again. But it is only experiments, not it's experience again, but not in the same, not in the same sense. So probably we can say this is robot learning or automata learning.
Yeah. But what about you? Like I was thinking, when child is born, child already has some, let's say, algorithm. I will use here this word, some mechanism to learn. Yeah? So child is already equipped with this active approach to learn.
Mm-hmm.
It's not intentional. It's not the child, of course, is aware of this, but it is seeking. It is, for instance, it starts to do babbling, blah, 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 and then when mother or father is selecting some words, child is following what is learning from parents, not from every possible stimulus, but specific stimuli. I thought maybe it is possible to develop algorithm not for doing specific things, but for activating search for learning.
Yes, yes.
Some kind of like meta algorithm. What do you think about this?
It's the life algorithm, I think. Yeah. Yes.
Do you see some kind of, is it completely out of question, or is it just possibility to search for algorithm to stimulate process of learning?
Yes.
Or indirectly?
Yes, exactly. But maybe I think it is the situation with robots, because thinking in the most randomly world, the robot has many possibilities to find any specific action. Again, the problem is that the number of algorithms is very ample, and inclusively, the robot choose a good algorithm, but maybe not the best algorithm. It is only for work in this moment and continue with the next action. Mm-hmm.
Okay, I'm just looking. Thus far, nobody raised a hand. Oh yeah, okay. Javier, please.
Yeah, thank you very much. So at the beginning of your talk, you mentioned von Neumann's original motivation of computation by unreliable components.
Yes.
So may I ask how you introduce unreliability into your theory or theoretical models, or how about your modular robots? What kind of unreliability appears in your modular robots?
Yes, it is because the consequence in several automata is immediately. You have only primitive signals where they will be some kind of self-organization to produce a stable component where can be manipulated to construct another complex component. So following this idea, it is possible to control a complex system and therefore implement a complicated components such a Turing machine itself into the cellular space. So, however, thinking how von Neumann was thinking the possibility to manipulate a natural process in the cerebral automata, was thinking more in the parallel process. not the linear computation that is the Turing machine. Because in this direction, maybe in server automata theory is always a recurrent problem why the computation will be following the linear condition and not exploit the parallel process. You know? In this case, for example, again, the majority gate is a nice example where the values are processed in only one step, and do not need wait 2 or 3 steps to get the final result of the computation. But yes, you are right. The modular robots were very useful to exploit this idea of parallel computation.
Okay, thank you very much. I don't see any raised hands. We have 2 more minutes. If nobody is asking questions, I have one general question which is not exactly related to your lecture, but I would like to tell you like in one sentence. Cellular automata were introduced by Ulam and von Neumann to escape complexity of continuous case. But actually, my question is this discrete character of automata, is it assets, something which is good, or liability?
I have only one comment here in this question, because sometimes, well, several times talking with many people in server automata, as indeed Adamaski, Katsunobu, Kenichi, Macintosh. Von Neumann has the conception of discrete domain, not because he had ignored the continuous domain. The motivation for von Neumann is only follow the most easy way, because the continuous version is automata increase the complexity to domain anything. It's only
yeah. The thing is that when we look now in hindsight, we can see that, for instance, introduction of calculus was a great, because many complex discrete cases could be resolved. Yeah, so we just instead of using, for instance, in probability, yeah, we have continuous distributions, like normal distribution is much easier than to deal with separate discrete cases. So in this case, I thought maybe some problems which are in cellular automata could be solved if we try to look for continuous case as some kind of going beyond what is. But actually, we got to the end of this hour. So I would like to thank you very much for a great lecture, very interesting. And what is important that you presented it in a way which could be understood by people who are not specialists in cellular automata, but still we could learn a lot. So thank you very much.
Thank you to everybody.